So hello everyone, this is a project CrystalClear, revolutionizing cataract prediction through transfer learning mastering. And about our technology, we have used transfer learning in this. The model is like adapting it to the another places. Like if it just train the model with the one task, in the few further task, it just adapts and uh, increases its accuracy. And this is a pre-trained model already. And why we are using the transfer learning over here is that the data scarcity, which means the hard to get the labeled data and the time efficiency of this model and model performance is better than the other models available, and the computing resources are of this model are much less than the other, so it will automatically give us the high speed of this model. And the project crystal clear, we have used four model buildings, which are namely Resonant 50, VG16, Efficient Net B1, and Inception. And over all these projects, the accuracy of ResNet 50 was the highest, which is 90%. So we have proceeded for the further task with using ResNet 50. And we have built the web using the Flask and the basic static HTML and CSS part for this. And coming to our vision of this project is to develop a future where everyone is happy in the and within we are committed to continuously improving our project or also our service, so that we can be upgraded with the current technology. And our mission is to like early in this particular project, our mission is to detect the cataract as early as possible so that you can get treated for this as soon as possible. And the current web, or you can say the project, is user friendly and innovative. You will even a child can just go and take it as a game or anything. And these are our teammates: Apurva S. Jagdishan, Shanmukh Sai, Maria, and Chandan Yadav.
So this is the home page. You can also go to the About page to read more about us. And you can also see Contact Us. So let's get started with the prediction. So we can choose a file from our local system. Say, let's just try the normal eye first. So the preview of the normal eye shows up over here. And you can click this button to predict if you have cataract or not. So as you can see, the result for this eye image is normal, and this is the confidence limits. So let's try again with the cataract image. Get started. So let us try with this. As you can see, the preview is of an eye with cataract. So the result is that this eye image, this person has cataract, and the confidence limits are 0.24. And for further action, if you require it, you can click on this button and it will take you to the link of a hospital webpage. And then you can further book your appointment. So I will be walking you through the code now of our cataract processing Jupyter notebook. And the first step was downloading the data set from Kaggle. So these are just commands for that. And then it downloads as a zip file. So you unzip the contents. So in case you want to see that, these are the contents being unzipped. The next is the data set which we chose is actually called the retina data set, and it has 4 categories of other retinal diseases as well. But since we are only going to be using the normal and cataract, I was just removing the other unnecessary directories. So this cell is to remove those directories. So after removal, we are checking the number of images and the categories which are left. So those are normal and cataract. And we have 300 normal images and we have 100 cataract images. And keep in mind that these are not split yet. So they're just in 2 folders. So next is the visualization part, which I use the OpenCV library for. So let's just see the visualization. So this is just one of the normalized fundus images which we have from our data set. This is the definition of the data augmentation layer. So what is data augmentation? We're going to be applying some transformations to our data set, such as flipping the image, rotating the image, zoom, and then changing the height and changing the width. So these augmentations are useful because when the model encounters real life data, it would perform much better. So let us see what an image which is passed through this augmented layer looks like. So this was one of my fundus images before augmenting. This is my fundus image like after augmentation. So you can clearly see that the scale over here is different and the scale over here is different. So transformations have been applied to it. So next, I was splitting the data into training, validation, and test directories. So training and validation is what I would be passing to the model, and the test remains unseen to the model so that it makes more accurate predictions. So I use the OS library to make these directories, and then I use the shuttle library to copy these directories from the source to the destination. And I created functions to do so, as you can see. So I prepared the training set with 240 normal images and 80 cataract images. The validation set was similarly prepared with 30 normal images and 10 cataract images. And test set was also prepared with the same number of images as validation set. So once this step was complete, the 3 directories were formed. So next we have data pre-processing. And in the data pre-processing, I just use the Keras pre-processing function. And over here, the image size was defined as 224 cross 224 because that is what the ResNet 50 model needs as input image dimensions. And I've defined the label mode as binary because we have a binary classification task in hand where the image is classified into a cataract image or a normal image. And batch size has been defined as 32, which means that in each batch, there would be 32 images. So you can see the output of this, that it has found 320 files belonging to 2 classes. This is with respect to training, and 40 files, 2 classes. This is with respect to the validation data. And then I was just printing out the names. So now we arrive upon the model building, for which I've used the Keras functional API. And I'm just importing early stopping and model checkpoint. So early stopping is really useful because say I train my model for X number of epochs. If it realizes that there's no improvement in the validation accuracy after a certain number of epochs, the training would stop. This would save me a lot of computation time. So here I've defined the base model as ResNet 50. And then I've also said include top is false because we are going to be defining our own output layers for the model. And this is what feature extraction of transfer learning does. You basically freeze the other layers and you just redefine the top layers. So this is freezing the base layers. So it says base model trainable is false. So I've defined the input layer. Next, I've applied the data augmentation layer. And next, I have used a global average pooling layer. And then I've defined a dense output layer. So this is the early stopping initialization, and this is for checkpoint. And this is the compile model step, where the loss is defined as binary cross entropy because you have a binary classification task. Metrics I've given as accuracy, and ADAM optimizer is what we're using. So I'm also saving it in a history variable. So we will be using this later to plot our graphs. And this is the fitting of the model for 50 epochs, but early stopping has also been defined. So you can see that the model got trained for these number of epochs, which is 6 epochs in this case. So next I save the model in H5 format. And this is me trying to print out the layers of the base model, which was ResNet 50. So let's have a look at that. You can see the convolution layers, you can see the batch normalization layers, you can see the ReLU activation function, and so on. So this is the model summary. we defined an input layer. We also defined a data augmentation layer. ResNet 50 layers, which we use from the functional API. And these layers are what we added extra, which was the average pooling and the dense layer. So now we will be using our model for prediction. So I just took a random image from my data set, which was one of a cataract eye. And let's see the output. So this was the image which I had used. So I'm saying that if the prediction is greater than 0.5, then the index is 1, which means that it's a normal eye. But if it's lesser than 0.5, the index is 0, which means that it's a cataract eye. And here, when I printed the same, it's a cataract eye for this image, which means our model is predicting correctly. So next, we move on to model evaluation, and we plot the loss curves. So I have two graphs over here. The first one is the loss curve, which shows the training loss and the validation loss for the epochs for which it was trained. So the second is an accuracy graph, which shows the training accuracy and the validation accuracy for the epochs. So that's it. That was the summary of the model. So that was Apurva. I hope you liked our project.
So this is Shanmugh. Thank you for watching.
Thank you.